This is Lab 9 Diffraction. I'm Owen Litt.
I'm Richard Pang, and this is for ITA Lam Nguyen.
Part A, diffractive apertures. The goal of this part of the experiment was to determine the diffraction pattern produced by different shaped apertures. This was accomplished using two lenses and a tube to send the light into the sensor. Results for Part A. These are the diffraction patterns produced by the single slit, the double slit large, and the double slit small. The images on the left are the Fresnel diffraction. The image in the middle is the image of the aperture, and the image on the right is the Fraunhofer diffraction. These are the diffraction patterns from the triangle aperture and the square aperture with the images following the same pattern. This is the data from the circular aperture with the three images at the top following the same pattern of the slides that came before him. The image scanned below them are the image from the actual data and sensor. The plateau in the data is due to oversaturation of the sensor.
Believe this.
We believe the secondary peak is due to stray light like ghost reflections. And overall, the data fit our functions well in both the vertical and horizontal direction, with the sombrero function being overall better.
This is Part B, beam profile measurements. The goal of this part of the experiment was to determine the beam profile of a Heaney laser. The beam profile was measured by a sensor and rendered on the laptop screen, and from our data we were able to calculate the numerical aperture, beam divergence, and waist diameter for the major and minor axis profiles. Part B, theory. We use a commercial beam profile to measure the beam width at full width at 13.5% max to then calculate other characteristics of the laser. We use the function omega z, and where zr equals pi omega naught squared over lambda, and we put our data into MATLAB and fit the curve omega z, where omega naught and z sub r were set as variable coefficients. And from this we were able to obtain values for omega naught, or the waist diameter of the beam for both x and y directions. Divergence angle theta could be calculated using trig and the difference between 2 points close to the end of the data, and then after calculating divergence angle we can find NA using the equation NA equals sine theta over 2. This is the code that we used. And for our results, these are two graphs produced for omega x direction and the omega y direction. We can see the fitted curves fit pretty well, and we calculate divergence angle for the x direction of 0.00196762 radians and NA of 0.00098 and a beam waist diameter of about 0.5 millimeters. For the y direction, we got a divergence angle of about 0.002 radians, NA of 0.00117, and a beam waist diameter of about 0.469 millimeters.